I'd like to now introduce the second technology that we'd like to present. The technology is a customized trackless mobile machinery collision prevention system digital twin. So that's quite a mouthful, but you'll get to read it again. I'd like to introduce my colleagues and the next speakers. Safiya, if I'd like to introduce you first. Safiya Turundu is our software developer in the CSIR mining team. She holds a BSc in computer science and an MSc in machine learning, with a focus on where she focused on fire detection for the University of Witwatersrand. And during her academic pursuit, she spent 2 years in the applied mathematics at the Academy of Sound Engineering, and spent another 2 years in the computer network as a computer network lecturer at WITS. So yeah, I would like to introduce you to the stage. And then her partner in crime, Fleckson, has more than 15 years of work experience in the mining industry. He holds a master's in mining engineering from the University of Wits and has a BSc in mining engineering from the University of Zimbabwe. He's a senior mining engineer within the mining cluster, and he has extensive experience across various areas, and I'll just take a few out. Product management, mining studies, feasibility studies, business improvement, research and development, and so forth. So please give them a hand, and guys, please.
Once again, a very good afternoon to you all. Thank you very much for attending our session. So in this presentation, I'm going to quickly allude to the background, and then also just to set the scene, what is the objective focus of the TMM digital twin. Then I will hand over to my colleague, Safiya, who basically take us on the digital twin data modeling as well as the simulation capabilities. So basically where this project started, this basically emanated from the engagement between the Minerals Council and the CSIR. That was sometimes in November 2020. And I recall very well when CITE challenged us to investigate the art of the possible regarding to how can the CSIR basically investigate the application of the digital twinning technology, basically to support the elimination of transport fatalities in the mining sector. I think as you can see from the first graph on the upper right corner, you can see that transport-related fatalities has been amongst the top 3 causes of fatalities in the industry. And as you can see from the 2 graphs at the bottom, during the previous year, that is 2021, TMM contributed to 7 fatalities, and for the year to date, TMM related fatalities has contributed to about 15% of fatalities in the industry. And in order to contribute to the industry goal of zero harm, that's ensuring that every mine worker returns from work unharmed every day, there was a need for us to see how can we also utilize some of the fourth industrial revolution technologies in order to assist the industry goal of eliminating fatalities and injuries. Then the second objective was basically to explore how can we also support the efficient operation of TMMs in the mining sectors, noting that South African mining companies are producing at high cost, and there was also a need to improve efficiencies and productivity in order to reduce cost. Then lastly, there was a request to also explore how can we support locally produced collision prevention systems, noting that currently most of the systems are also imported from overseas, and also in order to create to stimulate economic growth, it is important to also support the localization of the manufacturing and service industries. So in terms of the objective focus of the TMM, there was actually a task team that was formulated that was comprised of the CSIR research team, representation from the Minerals Council, as well as some industry experts to basically investigate the art of the possible regarding what can we actually do with the digital twin. So basically, these are some of the functionalities that were envisaged at the time by that tax form. So firstly, there was the desire to predict and detect unsafe acts and conditions, allow mining to to timeously implement corrective actions to prevent potential TMM incidents. So if you look from the accident causation principles, right, it is documented that about 80% of all accidents that occurs in any workplaces, including the mine industry, are as a result of unsafe acts. And the remaining 20% arises from unsafe conditions. So the capability to detect or predict these unsafe acts / unsafe conditions creates or offers an opportunity to the industry to take the necessary corrective actions in order to stop or prevent these accidents from happening. So that was one of the fundamental and most important envisaged functionalities of the tool. Then secondly, there was a request to see if we can achieve or provide near to real-time continuous safety risk management tool in order to assess and improve the effectiveness of the vehicle interaction systems. Then thirdly, there was a request to continuously and proactively identify high-risk areas and activities per shift, and also to provide a standardized safety risk assessment and quantification tool. So if you look at the current risk management practices in the industry, they are more reactive. That is, after the occurrence of an incident, that's when they do conduct the accident investigation to find out what went wrong. And then after that, they will have to learn from the incidents. But now there was a request that if we can have the capability to be able to continuously assess the risks, we will be able to put in place the right mitigation measures before all those unfavorable conditions actually culminate or result in an accident. And also, again, if you look at the current risk assessment practices, they are very subjective. And if you look at the law, specifically the Chapter 8.10 regulations, they say that where there is reasonable risk, then the mines must install level 9 collision avoidance system. But again, that's very subjective because how do you define reasonable risk? So there was a request that it would be ideal if there can be a standardized tool that can be utilized by the industry to perform this continuous risk assessment. Then other investigative functionalities was basically to optimize the traffic management systems in terms of safety, productivity, as well as operating cost. So as you can see from the diagram on the right-hand side, it basically depicts the strategic approach that was adopted by the CSIR team in collaboration with the industry regarding the development of the TMM collision prevention system digital twin. So during phase 1, that was from the period November 2020 to end of 2021. We basically demonstrated the proof of concept, where we basically demonstrated that the digital twinning technology can be utilized as a tool to predict the performance of traffic management system in terms of safety, in terms of productivity, as well as in terms of operating costs. So we are currently in phase 2, where we are basically piloting the digital twin at an operational site, and also other activities that will be involved during phase 2 include the migration of the tool to a cloud-based platform, application of a risk-based tool by the mine industry, as well as exploring other value adds functionalities of the digital twin, looking at things like predicting the emissions and so forth. And during phase 3, we envisage to support localized autonomous systems, which also links to some of the specifications that were indicated under the art of the possible. I will now hand over to my colleague, Safiya, to take us through some slides. Over to you.
Thank you very much. So, based on everything that Fleckson has mentioned, we can clearly see that a lot of investigation and research was done in developing this digital twin. And I come from the technology space. And in the technology space, there are many great ideas, but the challenge is transitioning from a great idea to a viable product. And we believe that after all the research and the development we've done, we have managed to change this digital twin from a concept to an actual implementation that can be used in the mines. So I'll start off by explaining what exactly the TMM, trackless mobile machinery digital twin, is. And it is basically just a virtual representation of trucks' behavioral pattern within the mines for optimizing operational flow. So if you have a look at the diagram here, how it works is data is extracted from the real world environment and undergoes a processing phase. And once this data changes into meaningful information, it is then used to model what we have, which is the digital twin model. And the virtual model is fed data to provide businesses with usage recommendations, which will help to enhance performance. The statistics that are gathered can be viewed by these businesses to help them in finding and implementing improvements at the mining sites. And the data is also useful for predicting future states. So for instance, predicting the likelihood of when or where an unwanted incident is likely to occur. And the main focus of this digital twin is safety and risk assessment. So one of the problem spaces that the digital twin focuses on is around traffic management plans. And the traffic management plan is basically an outline that describes a safe way for traffic activities to be conducted. Now, as you can see, there are various steps that are involved in developing and implementing this traffic management plan, all the way from creation to the implementation to monitoring the events while this traffic management plan is active, down to incident response. Now, the problem presents itself around the time delays that are incurred between each step. And when an incident finally occurs, a reactive approach is taken to deal with these incidences. Experts are brought into the scene to assess the situation in order to prevent this incident from happening again. And in many cases, you find that this risk assessment is subjective in nature. It's based on the experience and the expertise of the personnel that has come in to assess. Now, what the digital twin aims to do is to eliminate the need for this incident response by taking on a continuous objective approach in identifying these risks. And the whole point of this is to potentially eliminate the need for any incident response after any fatalities or any unwanted incidents has actually occurred. And it makes use of predictive measures to pinpoint exactly where and when these unwanted incidences are likely to happen. So the technical process involved with this digital twin involves extracting historical data to model the environment in which these trucks are interacting with one another. This data is then, data analytics is used upon that data to provide recommendations, which can be used to improve driver interactions during the course of their journeys. For instance, providing recommendations that will help to reduce traffic violations. And we also have various machine learning algorithms which can be applied onto that same data to produce predictions, which will investigate the likelihood of when and where unwanted incidents could occur, with the goal in mind of preventing such incidences from happening. And together, these two form a proactive intervention strategy. So currently what is being applied to the mining landscape is the risk matrix, which we have here. It's basically just a graphical portrayal of risk severity levels that are experienced within the mining site. And one of its main functions is to help identify areas of risk for risk reduction, as well as to identify and group these various risks based on their severity for further investigation. And these groups are basically prioritized based on their severity. One of the areas that's lacking in this risk matrix is the ability to forecast. And this is where the digital twin comes in as an augmented solution. It has the same goal in mind in terms of safety. However, it makes use of data analytics and modeling to be able to identify the particular areas within the mining site as well as their severity levels. And this gives the planning teams a futuristic view of how they can plan around these various risk factors. So the components which make up the digital twin involve the vehicle logs. This is basically the data that is ingested by the digital twin, and it is made up of longitude, latitude information. We also have the traffic management plan itself. We have operational practices which are focused on risk-based management. And the core of this is the digital twin simulation, which makes use of data analytics and machine learning to digitize these various components. So what we've done is we have separated the functions or the capabilities of the digital twin into 6 sectors, which we will go into briefly. But the center of all this is basically around risk management. So the first 2 sectors, which is the sensor and vehicle technology modeling, they speak to vehicle-to-vehicle and vehicle-to-pedestrian interactions for the purpose of collision avoidance. And the next 2 sectors are the mine layout and the mine traffic management modeling. And this speaks to multiple vehicle interactions as they journey upon this path within the same time period. And the reason for this is to be able to pinpoint areas along this path that commonly experience close interactions where risks are highly possible. And the last 2 is the statistical and machine learning, as well as modeling as a service. And what this does is it turns the data into insightful information that is able to be projected to the user. For instance, from this, we're able to get information in terms of the traffic flow within that region, or even the speeds that occur within that region, and able to then implement plans around such patterns. So right now we're just going to dive into the actual development. So what we have here is the digital twin, and this is just it is a cloud interface. And here we're going to just simulate the vehicle speeds that are experienced within this particular mining site. So as you can see on the left-hand side, there's a legend which gives you an indication of the various speeds that are experienced in this particular sample. And on the map itself, you can see the actual speeds that are generally experienced by the vehicles that have traversed upon this hauling road, or these different parts. So this is just one of the possible functionalities of the digital twin. And another important factor that needs to be monitored, of course, is the loading and unloading events. And what we've done is we've been able to extract the time frame, or the amount of time that it's taken for these vehicles to engage in the loading and unloading activities, as well as the time in which they spent traveling within that site. And this is useful in order to determine how active or how idle that particular vehicle has been during their work duration. And here we have the implementation of traffic management plans. And what we're able to do here is we're able to add in various traffic elements to the actual map in which these trucks are interacting in. And one such traffic element is a berm. We're able to place in berms, we're able to place speed zones and apply a particular speed limit within that region, as well as stop signs. And the reason why this is useful is because the user will then be able to simulate, based on these new additions, what the traffic flow will look like when this traffic management plan is implemented. So this is kind of a planning tool to assist the mines with developing the most viable or most reasonable plan for the various mining personnel to make use of. So there we have added the berm, we've added the speed zone, the user has just added a stop sign, and these are just a few of the things that the digital twin is able to do. And there the users added the maximum speed. So some of the events that the digital twin is able to capture includes vehicle interactions, close vehicle interactions within the mining site, anomaly events, as well as non-conformance events, which we will go into very briefly. In this example here, we have close vehicle interactions which are being experienced along this path. And as you can see, we have the yellow and red dots, which give you an indication of the severity of the close interactions that are being experienced in this particular environment. And here's an example of anomaly detection. So if you have a look at these two different paths in red and in blue, the blue is the path in which vehicles are commonly used. So this is the path which is expected to be used. The anomaly here is being flagged by this red path here. And what this indicates is that something may have occurred within this region to cause this anomaly. It could be an accident that may have occurred, which forced the vehicles to use the red path. It could be any kind of obstruction. But the main point around this is to be able to pinpoint and find these anomalies. The digital twin is able to do that. And this gives mining personnel insight in terms of what is happening within that mine site. And they can then go on to perform further investigations to find out why such an anomaly event is occurring. And here we have various unsafe conditions which are being detected. In this slide, we have the speed zone region in orange, we have the stop zone in red, and we also have the berm zone in yellow. What the digital twin is able to do is within these regions, it's able to pick up when non-conformance events are taking place. So in the areas that are flagged or highlighted in red, we see stop violations have occurred. And areas highlighted in orange are obviously referring to speed violations that have occurred. And we also have those in yellow, which refer to a berm or distance violation. And this is what the digital twin is able to pick up. So in conclusion, or in summary, the digital twin operates by using an optimization cycle. The data is extracted from the real-world environment. Data analysis is done to organize and extract this data into meaningful information, which is then used to generate our digital twin model. Further investigation is done upon this data by using machine learning algorithms that are able to process this information and generate the outcomes that we would most likely want to make use of. So it's able to generate various scenarios using these machine learning algorithms. And once the most needed or the most useful outcome is determined by these algorithms, it can then be transferred back into the real world environment and basically acted out by the various trucks that interact within that mine site. And this is how the digital twin works. So I will hand it over to my colleague Fleckson to just discuss the various benefits of this digital twin. Thank you.
Thanks, Safiya. I think from what has been presented so far, it's apparent that the digital twin project is aligned to the mining industry objectives. For example, there is the technology pillar that is contained in the culture transformation framework that was developed by the Mining Health and Safety Council, where basically it advocates for the use of technology basically to enhance the sustainability of the mining industry, that is improving productivity, improving operational health and safety, reducing operating costs, Then also looking at things like how do we improve the efficacy of the risk management process in order to improve health and safety. I think we are all in agreement that risk management forms the backbone of any operational health and safety management system. So we believe that these two is actually going to enhance the efficacy of the risk management practices in the industry. Also, in this slide, I'm just going to summarize some of the capability benefits of the TMM digital twin. So from a compliance benefit, the TMM digital twin is basically going to improve the safety of TMMs as well as the compliance, looking at things that ensuring that the mine put in place sufficient controls in order to prevent unwanted TMM interactions or accidents. I think from some of the demonstrations, which are basically outcomes of the modeling and simulations that were done, I think we managed to see what the TMM digital twin can actually do in order to assess the efficiency of the controls. Then also the TMM digital twin offers that flexibility to respond to changes without compromising safety and compliance. Then from a strategic point of view, the TMM digital twin can actually provide that dynamic traffic management. I think we understand that the mining environment is quite dynamic. I remember when I was at school, my lecturer always told me that mining is a very complicated process where the miner will always be in a different place from where he was yesterday. Because remember, the goal of mining is basically to advance. So the miner will always be at a different place from where they were. So it's quite a dynamic environment, and I think that's where the power of the digital twin comes into play. So the TMM digital twin can basically assist to predict the performance of traffic management system in terms of safety, productivity, as well as cost. That's providing input into short, medium term, and long term planning for greenfields and brand projects. So, for example, if at a mine you are maybe increasing the size of your fleet, you can actually run some simulations so that you will be able to predict what will be the envisaged performance of the traffic management system due to changes associated with the increase in fleet size. And you'll be able to put in place the necessary corrective actions. But in the absence of such a tool, you find that in most cases you are always caught by surprises because you are not anticipating anything. But this tool at least gives you that kind of comfort so that you'll be able to predict the envisaged performance of the system prior to introduction of the changes, and that this can actually allow you to put in place the necessary mitigation measures in order to ensure that you are not caught by surprises when you actually effect the changes. Then secondly, it also enables data-driven insights to enable continuous improvement of TMM safety, productivity, and cost. Then from an operational perspective, obviously the TMM digital twin is going to result in improved safety and as well as allow efficient maintenance of production. As we see from some of the simulations, it allows to predict / detecting unsafe acts and conditions. Says for instance, if you realize that driver X is always disregarding road rules such as not stopping at stop signs, overspeeding, and so forth, then you can actually come up with some customized behavior change or training interventions in order to make sure that you cultivate the required behavior in your drivers. And we believe that that will be a significant milestone and will go a long way to improve the safety of operation of TMMs in the industry. Because right now, I think a blanket approach is used to inform behavior change interventions as well as training interventions. But with this digital twin, it will give the mine management some insights in terms of which category of drivers maybe need to go for training on compliance, maybe related to overspeeding or maybe obeying road signs and so forth. And I would believe that is also going to save the mine with a lot of time and energy regarding the training interventions. On a concluding point, as we have noted earlier, phase one of the project basically demonstrated that the TMM collision prevention system digital twin can be utilized as a tool to predict the performance of a traffic management system in terms of parameters such as safety, productivity, and cost. Then it also offers an opportunity to continuously assess TMM collision risks, as well as to detect / predict unsafe acts. So we are currently busy with phase two, where we are conducting an operational pilot at an open cast coal mine in the Limpopo province. And we will be able to share the lessons learned from the pilot with the industry, of course, with the permission of the pilot mine. Thank you very much for listening to our presentation. I think we can open the floor for questions and discussion.
Thank you very much. I know we're literally eating into your lunchtime, but maybe just a handful of questions to start off with, and I'll just have a closing remark. Yes, yourself.
Thanks. To John, 2 questions quickly. You say that this is your Go Fawn is ready for manufacturing. Has it been through an industrialization process, or is there additional investment required to industrialize it?
Okay, so this technology is now at what we call TRL level 8, 9. Okay, so we would assume that, I mean, it's fairly industrialized, but it needs to be optimized a little bit according to requirements from service providers. So they may want certain types of branding, they might want a different shape, maybe different, like supports or and different interfaces. Right, so those kind of things still have to be done by our manufacturing partner.
Okay, great. Second question is, can it be applied to hard rock underground as well, or is it only optimized for coal mining?
The current device, it is in our plan to make something for hard rock mines called FOG1, but this is a device just for coal mining. So I mean, we believe that there's a lot of potential on this device. Like I said, that there's no competition in the world for this. And even if we look at the long wall mining operation, the kind of interfaces that you have, you can connect this to that continuous miner so that as soon as there's a go for warning, the continuous miner can stop operating, right? So that actually improves the safety. Now, if you look at the extension of coal mining, given our electricity situation and so on like this, your ability, for example, in your stooping operations to extract the coal pillar safely can actually extend the life of a mine by about 10 years, So this is very important decisions. And we believe that there is a huge market for this, not just in South Africa, all over the world.
Excellent, thank you.
We're also looking for anybody else who's interested in this as well.
I think we've got a question there in the back.
And Lewis, watch the space. There's still the ITAD coming out, right? Next year. Yes. So hopefully there will be a lot of devices coming out.
Just clarity from John.
Yes.
You said you are waiting for the license or the licenses.
No, we are licensing out the technology. So we don't want to be in the business of running around installing this, making this, because what is hitherto being the problem is that there's a lot of people who come knock on our door and say, we'd like 50 of these, please. And say, what can we do? So there has to be a manufacturing process. So we want manufacturing partners.
Okay, no thanks. I thought you said you were waiting for the license.
No. We will be giving a license.
Okay, hi everyone. For the digital twin guys, what sort of change management should be accompanied with the implementation of a system like this so that we don't find operators thinking there's a traffic cop on the mine all of a sudden?
Thank you. I think I will respond to that. Then my colleagues can also jump in. So I think my personal experience is that with system like that, I think it is very important. When a mine decides to implement this system, it is important for the mine to engage the employees So it's more of like doing a cost-benefit analysis where they have to detail in terms of what are the benefits of introducing this technology. I think one of the reasons why technology fails is that there will be fear of the known fear of unintended consequences and things like your mongering, where people will be gossiping in the streets to say, you see, this technology that they are bringing in, it's more of a witch hunting process. But I think the mind should make some efforts to debunk all those myths that might actually have any unintended consequences and at the end results in failure of adoption of the technology. So I think from a change management perspective, I think just to conclude, I think the critical thing is for the mind to engage the workforce in good faith, and also to make them understand what are the benefits of introducing this technology. I think the minds are aware that a number of lives have been lost in the industry as a result of TMM fatalities, and I think in my view that would be the best selling point. And once employees know that this system is there to protect us, to save our lives, to ensure that we will go back home from work every day, then I think definitely there will be buy-in from the workforce. I'm not sure if other colleagues would want to add.
I'm the chair, I'm not allowed to say anything.
Just a question from my side to the team. I mean, quoting from one of my colleagues' words, saving lives and saving livelihoods. We can see how the TMM, I mean, the digital twin is going to be saving lives, but how is it going to be used from the side of saving livelihoods, especially with the challenges that we have of unemployment in South Africa?
Okay, so if you look from our strategic roadmap of the development of the project, during phase 3, we are going to explore how we can also support the localization of manufacturing and service industry of the collision prevention systems. So in our view, that is going to stimulate economic growth, basically from the players that will be involved in the manufacturing as well as the service of the CPS unit. So we believe that it's going to assist in that perspective.
Can I maybe just also answer that? So in terms of the livelihoods, in terms of the livelihoods, one looks at the benefit of the operator actually knowing how they are driving. So I'll make an example with myself. Prior to load shedding, I mean, I would switch on the kettle iron whenever, it suits me. But following having a system that actually enables me to see how my usage is, I'm now more aware of how do I utilize my battery capacity to be able to optimize my energy usage. For instance, I mean, with my helper as well, she does it. She knows when the battery, she goes, she looks, the information is there. Now she's able to optimize on solar energy during the day to iron, and knowing how much the iron actually pulls. So to use that example in the mining industry, we're actually giving power back to the operator. He can see, or she is able to then monitor how is it that I am driving. And by the way, I mean, in the mines, you talk about reying tone. So if ever I know that I'm reying tone, but I'm doing it in a safe manner, it's improving my productivity, and thus I'm ensuring that, there is a productivity and maybe bonuses.
Thank you very much. I think that is pretty much the last question that we can take. Otherwise, we're going to literally eat into more of your lunch. We don't want that either. But I think just as a closing remark is to understand that if you look at the CSIR's mandate is really to uplift socioeconomic conditions in the country. And if I had to translate that in my world and in the way I see it, is we are doing RDI, technology development, to create jobs. That's basically it. Create jobs, create opportunity, create wealth for locals. Now, with that in mind, all the technologies that we work on, everything that we put forward, we will eventually make available to the market for commercialization, as you know, a lot of the questions were asked around John's technology, for example. So the TMM digital twin, for example, will be in the very same boat. The whole idea is to develop it to a point where we could essentially put it on a silver platter and then offer it to the relevant players in the market that are interested and that see value in the product. So that is really where we see it, and we're then hoping that, and the real goal is then to create jobs, skills, capabilities around this product and program so that the individuals can take it further, maintain it, and develop it into whatever it's going to look like in the end. So yeah, thank you very much for your time. Really appreciate it. Thank you, presenters.